everyone, welcome to my channel. Today in this video, we're going to see about the evolution of certain set of objects made by humanity to see the distant and past universe. Space telescopes. Let's start the video. A space telescope, also known as a space observatory, is a telescope located in outer space used to observe astronomical objects. The concept was first suggested by Lyman Spitzer in 1946. Space telescopes avoid many issues caused by Earth's atmospheres, such as the absorption or scattering of certain wavelengths of light, obstruction by clouds, and atmospheric refraction. These advantages enable them to observe dim objects during the day and avoid light pollution that affects ground-based observatories. Space telescopes are classified into two main types: those that map the entire sky, astronomical survey, and those that focus on selected astronomical objects or specific regions of the sky. They differ from Earth imaging satellites, which are directed towards Earth for purposes like weather analysis and espionage. The Orbiting Astronomical Observatory (OAO) satellites were a pivotal series of 4 American space observatories launched by NASA between 1966 and 1972. Managed by NASA Chief of Astronomy Nancy Grace Roman, these observatories marked significant advancements in space-based astronomical observations, particularly in ultraviolet light. The OAOs were instrumental in demonstrating the potential of space telescopes, paving the way for future missions like Hubble Space Telescope. The first OAO, launched on April 8, 1966, carried instruments designed to detect ultraviolet, X-ray, and gamma-ray emissions. Unfortunately, a power failure occurred before the instruments could be activated, leading to the mission's premature end after just 3 days. The power failure rendered the spacecraft uncontrollable, preventing the deployment of solar panels needed to recharge the onboard batteries, effectively halting the mission. OAO-2, launched on December 7, 1968, was significantly more successful. Equipped with 11 ultraviolet telescopes, it operated until January 1973. This mission led to numerous astronomical discoveries, including the finding that comets are surrounded by vast hydrogen halos, and the observation that the ultraviolet brightness of supernovae can increase even as their optical brightness decreases. These insights were crucial in expanding our understanding of these celestial phenomena. OAO-B, intended to carry 97 cm ultraviolet telescope, aimed to provide spectra of fainter objects. However, its launch on November 13, 1970 ended in a failure. The payload fairing did not separate properly during ascent, causing the excess weight to prevent the centaur stage from reaching orbital velocity. This resulted in the re-entry and destruction of the satellite and its $98.5 million project, later traced to a flaw in a $100 explosive bolt that failed to fire. OAO-3, launched on August 21, 1972, was the most successful mission of the series, named Copernicus to commemorate the 500th anniversary of Nicolaus Copernicus' birthday. It was a collaborative effort between NASA and the UK Science Research Council. It featured an X-ray detector from University College London and an 80cm ultraviolet telescope from Princeton University, supervised by Lyman Spitzer. Copernicus operated until February 1981, providing high-resolution spectra of hundreds of stars and extensive X-ray observations. Notable discoveries included several long-period pulsars and the confirmation that the most interstellar hydrogen exists in the molecular form. The Hubble Space Telescope, launched in 1990, is a vital research tool for astronomy. Named after Edwin Hubble, it is one of NASA's great observatories.
5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Mission Control, Houston.
All program. Roger, roll, Discovery.
The Space Telescope Science Institute, STSCL, selects Hubble targets and processes data, while the Goddard Space Flight Center, GSFC, controls the spacecraft. Hubble has a 2.4-meter mirror and observes in ultraviolet, visible, and near-infrared regions. Its orbit allows for high-resolution images without Earth's atmospheric distortion, leading to breakthroughs like determining the universe's expansion rate. Proposed in 1983 and funded in 1970s, Hubble was built by NASA with contributions from the European Space Agency. Initially planned for a launch on 1983, it was delayed due to technical issues and Challenger disaster, finally launching in 1990 with a flawed mirror corrected in 1993. Hubble is the only telescope designed for maintenance by astronauts. 5 space shuttle missions have serviced it, the last in 2009. Hubble celebrated 30 years in April 2020 and is expected to function until 2030 to 2040. Hubble's successors include the James Webb Telescope and the Nancy Grace Roman Space Telescope, expected to launch on 2027. Lyman Spitzer's 1946 paper outlined the advantages of a space-based observatory, leading to NASA's recommendation in 1962. Nancy Grace Roman played a crucial role in advocating for its development. Space-based astronomy began post-World War II with missions like Orbiting Solar Observatory. NASA's plans for large space telescope took shape in 1968, emphasizing crewed maintenance supported by the developing space shuttle technology. Budget constraints led to a smaller mirror and collaboration with the European Space Agency. Hubble's construction involved multiple institutions. The Marshall Space Flight Center oversaw design, Goddard managed scientific instruments, Perkin-Elmer built the optical tube, and Lockheed constructed the spacecraft. The primary mirror required precise polishing, completed in 1981 despite issues. Hubble spacecraft needed to withstand temperature changes and maintain stable pointing, It used multi-layer insulation, an aluminum shell, and a graphite epoxy frame. A nitrogen gas purge reduced the risk of water vapor affecting the telescope. Hubble's initial computers included the DF224 and NSS-C1 systems, with upgrades over time. It launched with 5 scientific instruments: the Wide Field and Planetary Camera, Goddard High-Resolution Spectrograph, High-Speed Photometer, Faint Object Camera, and Faint Object Spectrograph. The fine guidance sensors served as both a guidance system and an astrometric instrument. The STS-CL manages Hubble scientific operations located at Johns Hopkins University. Scheduling observations is complex due to Hubble's low Earth orbit, and its operation is monitored 24/7 by flight controllers at GSFC. The Challenger disaster in 1986 delayed Hubble's launch, grounding the shuttle fleet and increasing costs. The delay allowed for extensive testing and improvements before 1990 launch. The Chandra X-ray Observatory, launched by NASA on July 23, 1999, is a flagship mission dedicated to studying the universe in X-ray wavelengths. Named after the Nobel laureate Subramanian Chandrasekhar, the telescope orbits Earth in a highly elliptical orbit to avoid contamination from Earth's radiation belt and atmosphere, allowing it to observe X-rays with high sensitivity and precision.
6, 5, 4, 3. We have a go for engine start. 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
Houston, Columbia is in the roll. We've got a fuel cell stage number 1.
Roger, roll, Columbia, we're looking at.
Equipped with 4 advanced X-ray telescopes and imaging spectrometers, Chandra detects and analyzes high-energy phenomena in space such as black holes, neutron stars, supernova remnants, and hot gas in clusters of galaxies. Unlike telescopes observing visible light, which are limited by Earth's atmosphere, Chandra's X-ray observations provide unique insights into extremely hot and energetic regions of the universe. Chandra's scientific objectives span a wide range of astrophysical phenomena. It has observed the X-ray emissions from asserting black holes, revealing details about their environments and the powerful jets they produce. The telescopes has also studied the remnants of exploded stars, supernova remnants, tracing the dynamics of these violet events and the interactions between their shock waves and surrounding interstellar gas. One of Chandra's significant contributions to astrophysics has been the study of galaxy clusters, which are the largest gravitationally bound structures in the universe. By observing the hot gas plasma within these clusters in X-rays, Chandra has provided insights into the distribution of dark matter and evolution of galaxies and the cosmic web of large-scale structure. Chandra continues to operate well beyond its original mission duration thanks to periodic updates and maintenance. Its observations have led to numerous discoveries and deepened our understanding of the universe's most extreme environments. As one of NASA's great observatories alongside the Hubble Space Telescope and others, Chandra remains a vital tool for astronomers worldwide, providing crucial data for advancing our knowledge of high-energy astrophysics and the cosmic processes shaping our universe. The Fermi Gamma Ray Space Telescope (FGST), initially known as the Gamma Ray Large Area Space Telescope (GLEST), was launched on June 11, 2008 to conduct gamma ray astronomy from low Earth orbit. Named after physicist Enrico Fermi, this mission is a collaboration between NASA and the US Department of Energy, succeeding the integral mission as the most sensitive gamma ray telescope in orbit. Fermi's primary instruments, the Large Area Telescope (LAT) and the Gamma Ray Burst Monitor (GBM), study various astrophysical and cosmological phenomena, including active galactic nuclei, pulsars, high-energy sources, and dark matter. The LAT detects photons with energies from 20 million to 300 billion electron volts and covers about 20% of the sky, improving upon the EGRET instrument on the Compton Gamma Ray Observatory. The GBM, with its 14 scintillation detectors, can detect gamma ray bursts and solar flares across the entire sky, except where blocked by Earth. The spacecraft, built by General Dynamics Advanced Information System, operates a low circular orbit with a period of about 95 minutes, using a rocking motion to ensure comprehensive sky coverage. Fermi aims to understand particle acceleration in active galactic nuclei, pulsars, and supernova remnants, resolve the gamma ray sky, determine the high energy behavior of gamma ray bursts, probe dark matter and the early universe, and search for evaporating primordial micro black holes. The National Academies of Science prioritizes this mission, expecting numerous discoveries expanding our understanding of the universe. Fermi's instruments underwent rigorous testing to ensure resilience against launch and space conditions. Integrated with the spacecraft at General Dynamics Ascent Facility, these instruments provide publicly accessible data through the Fermi Science Support Center along with the data analysis software. The mission's initial 5-year lifetime has been extended beyond 10 years, with significant discoveries including a gamma ray pulsar on the CTA1 supernova remnant, observing the gamma ray burst GRB 080916C, and discovering a gamma ray surplus from the galactic center. In February 2010, Fermi confirmed that supernova remnants are cosmic particle accelerators. The mission has provided insights into the gamma ray background radiation, identified Fermi bubbles extending from the Milky Way center, and observed high energy light from the sun during a solar eruption. Fermi has contributed to understanding terrestrial gamma ray flashes, observed GRB 130427A with a record-breaking gamma ray energy, and detected a gamma ray burst coinciding with the gravitational wave event GW150914. The LAT instruments have received upgrades such as the PAS-8 software upgrade, significantly improving the data analysis and expanding the energy range for useful observations. The James Webb Telescope, named after NASA's second administrator James E. Webb, stands as a testament to human ingenuity and our insatiable quest to unravel the mysteries of the cosmos. Unlike its predecessor, the Hubble Space Telescope, which primarily observes visible and near-infrared light, JWST ventures into the realm of infrared astronomy, enabling to peer into the depths of the universe and unveil objects that were previously shrouded in darkness. JWST, collaboration between NASA, the European Space Agency, and the Canadian Space Agency (CSA), is an engineering marvel Its primary mirror, a revolutionary 6.5 meter, 21.3 foot primary mirror composed of 18 hexagonal segments made of lightweight beryllium. These segments unfold like origami after launch, precisely aligning themselves using ingenious micromechanisms. This giant mirror boasts a light collecting area over 6 times that of Hubble, making JWST a powerhouse for infrared astronomy. Visible light interacts with dust and gas in space, making it difficult to see distant objects, but infrared light with its lower wavelength can penetrate these cosmic roadblocks. This allows JWST to observe galaxies born just a few hundred million years after the Big Bang. For example, JWST captured the deepest infrared image ever, revealing galaxies dating back 13.8 billion years, a mere 350 million years after the Big Bang. The atmosphere of planets orbiting distant stars are thin and faint. By studying the infrared light they emit, JWST can identify the presence of molecules like water vapor. In August 2022, JWST detected water vapor in the atmosphere of exoplanet LHS 3844b, a discovery with major implications for the search for habitable worlds. JWST has peered into the dusty environment where stars are born, revealing never before seen details of the birth process. Its infrared views allows it to see through the dust and gas, providing astronomers with a clearer picture of how stars and planetary systems are born. The telescope can penetrate deeper into the dust, allowing us to see the formation of new stars within these pillars. JWST is still young, but its discoveries are already transforming our understanding of the universe. With its groundbreaking mirror technology and infrared capabilities, this space telescope is poised to answer some of humanity's most profound questions about our cosmic origins and the potential for life beyond Earth. These iconic pillars of gas and dust in the Eagle Nebula were previously imaged by Hubble, but JWST's infrared vision reveals them in a whole new light. I hope this video on the evolution of the space telescopes and observatories was interesting and informative. I'll meet you in the next video with another interesting module. Take care, bye.